All right, we're going to get one more look at another series inductive circuit. I'll get some more parallel circuits out there, but a lot of this stuff is going to be very similar as you work out through today. But what I did see is a couple guys getting stuck on these ones where they gave you a power factor and very little other information to start off with in solving some of these circuits. So if you had the power factor, but all you had was your henries and your voltage to start off with, we're going to look at exactly what we could do with that, what information we could draw from there. So initially this one looks a little bit difficult, but it's not too bad. But again, as before, let's just start off with converting this into something we can plug into the circuit, and then we'll just see what we have at that point. So if we're looking at our henries and looking to find out what kind of inductive reactance we have there, we can go ahead and remember our formula here. So if we are looking for the inductive reactance, 2 pi times the frequency times inductance. So 2 pi times 60 in this case, and we're just going to write this in as it would be. So millihenries, so I'm going to write it out, even though you could just put it in scientific notation form. And we'll go ahead and plug that in and get our inductive reactance to start off. So 2 pi times 60 times 0.079577. And that's going to give me pretty darn near 30 ohms. So 30 ohms. Now from this point, it looks like it could be a little confusing. You may have thought you didn't have enough information to solve this, but it's not exactly the case. And we'll look at our formula sheet to kind of remind us of why. So in a series circuit, we're looking at all of these triangles in here as part of our formulas or tools for solving this. And there's a phase angle in each and every single one of these. Now we don't have that yet, but that's just an observation. And then for the voltage or the impedances or the power, that phase angle is true. So coming back over here, is there any information I could use to get this phase angle? Well, the answer is yes. You have your power factor there. And remember that power factor, even though we don't know what the power, true power and apparent power are, we know what the factor or what the ratio of those two was to each other. And in trig, that ratio is all that really matters. So the only reason we're dividing those two numbers is to get a ratio, which is that 0.8. So whatever those numbers were that we don't have, the total to that division problem would have been 0.80. So if we were to take the cosine and put in the answer to the true power divided by the apparent power, that would be just like us dividing those sides that we haven't solved for yet. And again, this 0.80 power factor could be the same as, 8 over 10 or 80 over 100. And so it's going to cover any solution as long as the proportions of that triangle didn't change. And we know that that angle is going to be the same no matter what, as long as we know the length of this side and how it compares in proportion to the length of the hypotenuse. So with that little detailed kind of overly explained explanation, we can pretty much just take the inverse cosine and plug the power factor ratio right into that. And so let's go ahead and do that and see what we get. So inverse cosine of 0.80, and we get 36.870 degrees. All right, so now that I have that angle, what can I do with that? Well, let's go ahead and draw our impedance triangle here. So I have one value for that impedance triangle, and that is the opposite side of the angle, the phase angle. So I have a 30 over here, and I don't have any of the other values. I don't have my resistance value or my impedance. But I do have this angle. So just like in trig, when we gave you guys a bunch of those problems, you can solve for any missing values in a triangle as long as you have two values, and we do have that angle. So knowing the opposite, I could solve and acquire the resistance, which would be the adjacent, and the hypotenuse, which would be the impedance. So let's solve for those using that method. So if I had we'll say sine. We'll do opposite over hypotenuse first. So sine of 36.87 degrees is equal to 30 over my hypotenuse, which I don't have yet. So through substitution, we know when we move this around, if we want to get the hypotenuse, it's going to look like this. And so let's see what our impedance is based on that calculation. So 30 divided by sine 36.87. So that gives us 50 ohms for our impedance. Now, once you have that, you can use your Pythagorean theorem, but since we already have these values, let's go ahead and use the same numbers again to solve for the other side of that triangle. So let's find out what the resistance would be. So the resistance would just be tangent, right? Because we'd be doing the opposite and the adjacent. So either way, the opposite is still going to be on top. So I could say that my tangent of 36.87 is going to be the same. It's going to be 30 over my adjacent. So it's going to look just like this, but it'll have tangent instead of sine. So let's see what that looks like. 30 tangent, 30 divided by tangent 36.87 gives me 39.9. Okay, so we're going to say 40. So approximately 40 ohms. So with all these values, now I can start doing more of this equation here. I have all my impedances, so I can now find my current. So 100 volts divided by 50 ohms is going to give me 2 amps. Now, in a series circuit, the amps are the same all the way across, right? So now we're right back to where we were on the other one we solved for. So now I can solve for the voltages, power, I can get all these values. There's a couple different options on how you can get them too, since we have so much information at this point. So let's solve for the resistance drop, voltage drop across the resistor, which is going to be the current of 2 times the 40 ohms. That's going to give us 80 volts. And the 2 times 30 ohms is going to give us 60. And so we have a voltage drop of 60 and 80. Now that doesn't add up to our total voltage drop of 100, but remember, we're not looking at the DC anymore. So if we're looking at our trig triangle here, we could use Pythagorean theorem to check for your work and make sure that the voltage drops that we got are true and that they do add up to the total voltage. And so let's see what that would look like. So if I had Pythagorean theorem, I would take 80 squared plus 60 squared, and I would hope that that would give me 100. So let's see here. Yep, so that our work checks out there. So everything up until this point has been pretty good. Now all we have to do is solve for our voltamps, watts, and vars, so our power. So the easiest way for me to do that is just to take the voltage and the current, because there's no radicals, there's no division, it's just the volts times the amps, and that always gives you the power, right? So 100 times 2, I can already see that that's going to be 200. 2 times 80, so I'm going to have 160 watts, and 60 times 2, 120 vars. Now again, to check your work, you wouldn't just be adding those up like in DC, but you could be using your trig triangle and use Pythagorean theorem to check your work for that. So again, let's do that again. We're going to take 160 squared and 100 plus 120 squared, and we're going to find the square root of that. And that gives us 200. So far we've checked a lot of our work up to this point, and there's one other thing that you could check here as well. So we checked to make sure our voltage total is correct. We know our current is. We used Pythagorean theorem to get our impedance, and now we use the same thing to check for our voltamps, our power. There's one more thing we could check for, and that's going to be our power factor. So based on what I know, my watts at this point divided by my voltamps should equal the power factor, which I started with in the very beginning. So 160 divided by 200 gives me 0.8, an 0.80 power factor. So it all came back full circle. Checked our work. We used our power factor to find our phase angle. We used that in accordance with the inductive reactance, which we found from our Henrys, our inductance that we started off with. And the only other thing we had was the voltage total. So we came a long ways from that with very little information, and I hope that clears up a little bit on how we got to that point. I'll go ahead and take a look at doing some of the other homework assignments, and then maybe some other problems more on par with what we'll be doing later this week. All right, tune in again next time.